Hello students, in this video we'll prove the identity theorem for holomorphic functions. Let's get it set up. So let's let f map omega into c be holomorphic. We know this automatically implies from the previous video that the f is complex analytic, right? And omega a domain. Domain is just a fancy word. You see this in like all the classical complex, old school complex analysis like Alfors and Rudin in Saracen's books. So if you look at the old school complex analysis, they use this notation a lot. Domain just for open and connected. Okay. Connected is an essential part of this, right? Because, for example, you can have a function which is identically 0 on one set, and on a completely different component, it can be identically equal to 1. That function is still holomorphic, right? So connectedness, it plays an essential role in this argument, okay? Holomorphic and connected. And let's consider the set ZF. ZF is what? It's the set of points Z and omega, such that f of z is equal to 0. And so, of course, this set ZF we know from analysis. So if I choose a sequence of points that is 0 by the continuity of f, this set is closed, right? It's closed in omega, right? So by continuity of f, since it's holomorphic, it's clearly continuous, right? Remember that result from calculus, if you're differentiable, complex differentiable, you're automatically continuous, okay? Good. By continuity of f, ZF is closed in the subspace topology of omega. In other words, the open sets in omega are just the open sets in C, just the disks, intersect with omega, right? So you might get some funny thing that has the boundary component to it, okay? Good? So that's the first thing we have over here, closed. Now I need a slight review of some facts from point set topology, for metric topology, right? So recall, Z0, the point in Z0 is an interior point. We'll define interior point first of a set E, which is a subset of C. If what? If there is a disk, if there is an R, if there exists an R greater than 0, such that what? So there has to be an R such that dZ0, the disk centered at Z0 of radius R, is contained in omega. In other words, I can put a little disk inside to omega. Excellent. That's what it means to be an interior point. Or not omega, but E, sorry. We're doing it just for a general thing, just for E. E, good. That's what an interior point is. What is a limit point? Z0 is a limit point or accumulation point of E if for every R greater than 0, there is this disk dZ0R contains a point W such that W is not equal to Z0. In other words, every neighborhood of this point Z0 has a point from the set E that is not the point itself, right? That's not Z0 itself. In other words, there has to be, in a metric sense, there has to be a sequence of points, call them WK, that converge to Z0. That's what it means in the metric sense. So in the metric space set, I can find a sequence that does this, right? Or, yeah, good. Okay, excellent. And then finally, a point Z0 is isolated from E, is an isolated point if it is not a limit point. And remember that closed sets are the sets that contain what? Closed sets are the sets that E is closed if and only if E can get written as E union the limit points. In other words, the limit points has to be a subset of the set itself. Good. Okay. That's a little bit of just point set topology in the complex plane. Excellent. Okay. Now let's proceed. Okay. So here what we're going to do. Let's first suppose that that Z0 is not what? Is not in the interior, an interior point of ZF, okay? What does that mean, okay? Well, we know F is analytic. F analytic implies what? Implies that F of Z is equal to the sum, n goes from 0 to infinity, of a n, and then z minus z0 to the n. Okay? And then what can we do over here? So now over here, z0 and f is not an isolated point. So let's look at a point in z0, but I'm assuming that this is going to be in zf, right? So it's the root of f. So what happens is that if all of the an's are 0 in this expansion, if every single an is 0, then f is identically equal to 0, right? So this is valid in some small ball, right? Okay. That would force f to be identically 0, which contradicts the fact that it's not an interior point. Because if f was identically 0, right? So if all an are 0, if all an for all n, then what? Then f of z is identically 0 on this disk over here, on z minus z0 less than r. And that contradicts the fact that you're not an interior point, because that means there's a little disk that's contained in the, that forces z0 to be in the interior of the 0 set, okay? So in other words, there has to be a smallest n. There's a smallest n in n, such that what? Such that f of z is equal to a n z minus z0 to the n. So I factor that term out. And then that was the first term that was non-zero, so that corresponds to a 1, right? That's the n capital term. Then plus a function g of z minus z0 that tends to 0, right? That tends to 0. And then g of z minus z0 approaches 0 as z goes to z0. Okay? Now, of course, this function over here, z minus z0 to the n, this thing has the only root of this is z0. So z minus z0 to the n only has a root at what? At z0. And this implies that f is not 0, so hence f of z is not equal to 0 in a small enough neighborhood close enough to z0, in some neighborhood of z0. And what does it say? It says if you're not an interior point, that says that this z0 is isolated. So z0 is an isolated point, isolated of the set, 0 set. Okay, so the z0 is now isolated. Okay, so now we have two cases. So hence, this 0 set is the set of isolated points of ZF. Either you're isolated, ZF, okay, or you're what? Or you're interior, right? Or you are an interior point. The interior of ZF, okay? Now, automatically, the interior of ZF is an open set. Interior of ZF is an open set. Why so? If I give you any point in the interior, that means there's a small enough ball or disk that's also contained in that set, which is the definition of what means to be open. Okay, so that's by definition, right? So this is by definition. Okay, excellent. And now let's let W be a limit point of interior of ZF. Now remember that the interior of a set also contains the set itself, right? So that means there's a sequence. There's a sequence ZK in the interior of ZF such that ZK converges to W. Okay? Well, f of ZK is 0. So by continuity, f of w is 0. And that forces what? That means now, of course, this f of w cannot be what? I cannot converge to this. The w cannot be a what? W cannot be, this implies that w is in ZF, but w cannot be an isolated point, not isolated. Why not? Because a sequence of points in the set, by definition, cannot get arbitrarily close to an isolated point, because the isolated point is a neighborhood where there are no other points of the sequence in that set. So the sequence cannot converge to any isolated point. What does that prove? That proves that this WF is closed. So the interior of ZF is open, and interior of ZF is also closed. Interior of ZF closed. And that implies, now the set is, the interior is open, it's open by definition, and it's closed. Open and closed, if you're in a connected set, the only open and closed sets there are is either the empty set or the identity, right? So this implies that the interior of ZF is either empty or it's all of what? It's all of omega, okay? Now, if the interior of ZF is empty, that means all of the zeros of this holomorphic function are isolated. So this is all isolated. These are all isolated zeros. And this is everything, right? Okay? So either the zeros of an analytic function, and this is the identity principle, right? The identity principle says that the zeros of an analytic function are either all isolated points, or the function is identically zero. So in other words, if there's a point of accumulation, so if there's a sequence of zeros that converges to a point in the domain, then the function has to be identically equal to zero. It has to be zero everywhere. And that is the identity principle for holomorphic functions. It's a very, very useful mechanism when you're trying to compare two holomorphic functions. If, for example, you can show that two holomorphic functions agree on a set where there's a limit point, then those holomorphic functions have to agree everywhere in the domain, which is a beautiful result. So in other words, if I can sample a countable number of points that has a limit point, and two holomorphic functions agree just on that sequence that contains a limit point that has a limit, they have to be equal everywhere on their common domain, right? In other words, they have to, that identity extends, that's why it's called the identity theorem, right? The identity on a discrete set, a countable discrete set that has a limit point, forces the functions to be identically the same. Very, very useful mechanism when you're trying to prove it, in particular on qualifying complex variables qualifying exams. Very, very useful mechanism to solve a wide variety of problems in complex variables. Thank you very much.